Okay, so we left off looking at this question from the study guide, number 25. Which reaction would yield a meso product? So I'm actually going to run through all these scenarios with you. So let's go over here and we'll just try them all. So this is question number 25. And A said we were starting it with cyclobutene, right? So you have cyclobutane, so this is cyclobutene. And then it says if we're treating it with water and H plus, that's the same thing as saying H3O plus. Now in this case, both carbons that are sp2 hybridized have one hydrogen attached to them, so there's no Markovnikov or anti-Markovnikov. You're just going to get the hydroxyl added to one of them and then a hydrogen to another. So this is not a meso compound. So not meso. Okay, there's no stereocenter in here. Then if we look at B, it's bromination of the cyclobutene. So just using bromine. They put a solvent. They put CCl4, which is carbon tetrachloride. But you guys all know that this gives you anti-addition. And so you'd get this plus the enantiomer. And so this is not meso. These are definitely, there's no plane of symmetry here. Then if we go to C, C is in the same vein as the first one. You're just treating it with HCl. There's no Markovnikov. There's no anti-Markovnikov. You just get this. So this is not meso. So it better be the last one. And the last one, the reason I wanted to go over this one in detail with you is because it's using deuterium, right? D2. So remember, deuterium is nothing more. You can treat deuterium and platinum as if it's H2 and platinum. You can treat it the same way, but we know it is syn addition, right? That means that both deuteriums are going to be added to the same face of the molecule. So we're going to end up with one deuterium going down and the other deuterium going down. And you can see that there are two stereocenters and there is a plane of symmetry here. And so this is the meso compound. So that is the correct answer. So remember for the third time today that deuterium is just, sorry, I should put, deuterium is the same thing as hydrogen 2. Okay, it's just an isotope of hydrogen where you have one neutron in the nucleus. So question 25, there you go, and that is the meso compound. Now let's switch gears and get into some chapter 7 chemistry. We're going to go over to the section on nucleophilic substitution. So I wanted to start with question number 1. Okay, we'll start with question number 1. So this is some lighter fare. Some questions are so, not silly, but so straightforward that, like I said, you can answer them in a couple of seconds. I'd say this one would be in that vein, maybe. So here, if we have 1, 2, 3, 4, 5, 6, right? So you can see that this is 2-hexyne is the molecule, and it says, which two reagents could you mix together and end up with 2-hexyne? Well, if we look at number 1, we have the carbanion here, and that would do an SN2 here. I don't like it when my students draw mechanisms like this, but anyhow, you can see that this would give you the correct compound, so that better be the right one. Does anybody notice the problem with B? There's a major problem with B. There's nothing wrong with the nucleophile and the electrophile, but there is a major problem with B. Exactly. Thanks, Jenny. This one only has 5 carbons, right? And we need 6 carbons. So that's a big no-no. Jenny, did you notice anything about C? What the problem with C was? Or anybody? Anybody notice the problem with C? Yeah, it's got 7 carbons, yeah. And then D, well, that's got a major problem is there's no reaction. That's just 2 hydrocarbons, that no reaction whatsoever is going to happen. So no reaction. So if you're looking at this going, and that's it, you know, it's just the correct number of carbons. This one has 7 carbons. Yeah, pretty much in this one. Okay, let's take a look at question number 6. Oh, you know what? Let's take a look at this one. You know what? Let's look at question number 6 first. Then we'll come back to that one. Question number 6 is a good one. It says, what would be the major product of dehydrohalogenation? So if it's dehydrohalogenation of 3-chloropentane by KOH, so dehydrohalogenation, it means you're losing a hydrogen and a halogen, so you're going to lose HCl, right? Because the halogen is it's 3-chloropentane. So if we have 1, 2, 3, 4, 5. If we have 3-chloropentane and we're treating that with KOH and we're losing HCl, so this is an elimination reaction, what would be the major product? Well, you can see that you would end up abstracting this proton, right? The hydroxide ion would end up doing what? It would abstract the proton, form the double bond, lose the leaving group. And so you'd end up with 2-pentene, which is this compound here. Now, it doesn't, none of these are cis or trans, but you can see it's definitely not this, definitely not this, and definitely not this, right? So the answer has to be D. Now, trans would be the major, but again, here it doesn't tell you whether it's cis or trans. So there you go. So just a dehydrohalogenation. I think that one's relatively straightforward. But I want to take a look at number 7 because I think it's a little more complicated, okay? And this isn't one of the ones that I had on the list, but I think it's a really good problem. Okay, so if we take this secondary alkyl halide, okay, so if I draw, if I maybe draw a simpler bond line structure, right, you have a methyl group pointing up, and then you have a bromine pointing up, okay? So, and I treat that with KOH, okay? So what are my products going to be? Well, you notice that there's no substitution products here, none. These only have double bonds. So that means they're only talking about elimination. You would get some substitution as well here, but they're just saying, what are the elimination products? That's it. So if the bromine, remember that the bromine and the hydrogen in the leaving group have to be anti-periplanar. So anti-periplanar. Okay, so that means if the bromine is up and axial, that means that this hydrogen would be down and axial, right? This hydrogen here would be down and axial. So could an elimination reaction occur there? And the answer is absolutely. And if it did, you would end up with this compound where you'd have the double bond here, but you'd still have your methyl group. So you can see that that compound is shown here, here, here. So we can cross off A, okay? Now, as far as the other beta carbon, there's also a bromine going down here. So if this is up an axial, this would be down an axial. And so you could abstract a proton there as well. And so that would give you this compound, okay, where now the methyl group technically would be pointing up, but they haven't put any stereocenters in here. So we'll just draw it like that. So that means we would get both of these compounds, this one and this one. This is nothing. We would not get any compound like this. And this is not the only compound we would get. And so the answer is B. You would end up with both of those compounds. Yeah, there we go. All right. Give me a thumbs up if you follow me on the rationale for that one. Is everybody with me on that one? Because the one that I had put in the list of problems was this one, which is very similar, okay? So here, okay, so I don't want to bore you, but this one is in very much the same vein as number 7. Number 9 says if you take this compound here, right, if I draw a simpler bond line structure, let me draw it for you. You have the bromine up, and then you have the methyl group down. It's not my prettiest work, but anyhow. So then it says if you treat this with KOH, what do you get? Well, remember, they're only showing elimination products here, no substitution. So if I put this proton up, can I get an elimination reaction here? The answer is no, it's impossible. Because if this is up and axial, this would be up and equatorial. But if the bromine is up and axial, that means that this hydrogen here would be down and axial. So down, come on, Mr. Dion, down and axial. And so could I get an elimination reaction occurring there? The answer is absolutely. So in this case, the only compound I'm going to get is going to be this one. So I would get A only in this specific case, okay? So if you have to go back, remember that the leaving group and the proton have to be anti-periplanar to each other. Okay, let's try number 16. I wanted to look at number 16 with you. Number 16. It says, if this alcohol is dehydrated, which alkene is likely to be formed in the largest quantity? It's a good question. because, you know, it's just asking you which one's going to be formed in the greatest amount. So do you guys remember what kind of alkene we're going to get? We treat an alcohol with sulfuric acid. I told you this was one of my favorite reactions. They didn't include heat here. It's neither here nor there. You don't always have to heat it up, but you could put heat here if you wanted. Would I get the most substituted alkene or the least substituted alkene in this case? If I do the dehydration, right? Because you see that all of the answers are alkenes. So this is a dehydration. Would I get the most substituted alkene or the least substituted alkene as the major product? Anybody? It's going to be the most substituted alkene, okay? So if I take a look at all the answers, I think the best thing to do then is to draw a mechanism for this one if we're not sure. So let's draw a mechanism for this. Come on. Here we go. So let's go over to a blank document and we'll draw a quick mechanism for this reaction. So I'm just going to do it using a bond line structure just to make life a little bit more convenient. So the compound they gave us was this, I think. Yeah. And then you have a hydroxyl group. Okay, so this is the compound they gave us. And they said you're treating it with sulfuric acid. And so the first thing that's going to happen is you're going to protonate. I'm kind of drawing an abridged version of the mechanism here. But the first thing that's going to happen is you're going to protonate. So that means the hydroxyl is going to become a good leaving group. And so you're going to end up with this. Okay, so you end up with something that looks like this, where you have this secondary carbocation. And then you're going to get a methyl shift like that. And so then you're going to have this compound, right? And you're going to have a positive charge here. And so in the last step, what's going to happen is you're going to abstract this proton with your water to regenerate your catalyst. So you're going to abstract this proton and you're going to form the double bond. And so you're going to end up with this compound. I'll draw it like this. There you go. So that's going to be your final product, which is the most substituted alkene. So this is going to be the major product of the reaction. And so if we go back to the answers, if we go back in here, where was I? I was somewhere over here. You can see even if you don't draw the mechanism, you can see this is the most substituted alkene that you would get. All right. Let's move on to number 17. Let's take a look at this one. Number 17, fast question. It says if you're doing a dehydration of cyclohexanol, so now that you know how to name an alcohol, cyclohexane, that's all it is. Get it? Wait, let me go back here. Where was I? Cyclohexanol. And we talked about alcohols and dehydration. So if you have cyclohexanol, which is this compound, and if you're doing a dehydration with sulfuric acid, so H2SO4, you're going to end up with cyclohexene, right, after you lose H2O. Could anybody tell me what the first step of this reaction would be? Would it be loss of hydroxide, loss of a proton, formation of a sulfate ester, or protonation of the alcohol? Which one of these looks like the most reasonable first step for my elimination? Is hydroxide a good leaving group? I would say no. It's not a leaving group. And I'd say loss of a proton by the alcohol. I mean, why would that happen? You'd have to have a base to do that. Okay, you'd have to have a base. So a base would remove a proton. So that's definitely not it. Formation of a sulfite ester. We didn't even talk about sulfite esters. I don't know why you would do that. The first step is protonation of the alcohol, right? Right? Because then you take a poor leaving group and you convert it into a good leaving group. We've seen this many times this semester, okay? So then you would form the carbocation, right? And then you can do the elimination after that. Then water is going to come in as your base. and it's going to abstract this proton in your form like that. There you go. Yeah, anyhow. So let's just say proton transfer to convert a poor leaving group into a good leaving group. Does everybody remember this? Taking a poor leaving group, an alcohol, and converting it into a good leaving group? Okay, so just to review, again, an alcohol, a hydroxide, this is a poor leaving group. And then if you protonate it, okay, this is a good leaving group. Let's try number 20. Number 20, it says, which of the mechanistic steps shown here is not a reasonable one in the mechanism to describe the formation of 2-methyl-1-butene from the dehydration of 3-methyl-2-butanol? Okay, so going from here to here, you can see that this is not going to be a major product, right? It's some kind of Hoffman alkene, but anyhow, we're still going to form that product. And remember, the first step is that this alcohol, this is a poor leaving group. And so the first step that's shown here is it's been converted into a good leaving group, and then it leaves. So that doesn't look unreasonable. So I'd say that one looks okay. Here, this is a proton transfer. So here we'll put LLG. That looks reasonable. This one here is a rearrangement to form this tertiary carbocation. That looks reasonable. There's nothing technically unreasonable about this rearrangement. I mean, but a primary carbocation is pretty unstable, and there's no reason for this to happen because there's no double bond down here. So I'd put a big no on that one. And then the last one shows the formation of the double bond where we want it. So that one looks reasonable too. And so the answer is going to be C, is the unreasonable one. It has nothing to do with the formation of this product, right? There's no double bond down there. So totally unreasonable. Let's try number 30, which involves a ring expansion. Another one. Okay. So this one here, number 30, it says, what is the major product of the reaction shown? So this one involves another ring expansion that I showed you earlier today. So I just want to go over the mechanism with you of this one. So the first step, remember the hydroxyl group is a poor leaving group, so you convert it into a good leaving group by protonation. Then it leaves. So once it leaves, you would end up with this carbocation, right? Or you end up with this secondary carbocation. And so what's going to happen is the ring is going to open up because remember, a 5-membered ring is going to be more stable than a 4-membered ring. And so now if we count our carbons, if we count 1, 2, 3, 4, 5 like this, we're going to get a 5-membered ring like this. And then if I put my numbers in again, 1, 2, 3, 4, 5. And now the positive charge is going to be on carbon number 1 like this. And so now the bromine can come in and it can attack, or the bromide, I should say, and it's going to give us compound C. So the bromide is going to come in and it's going to attack where that positive charge is, and we end up with compound C. So remember, this is a ring expansion, right? And a 5-membered ring is going to be much more stable than a 4-membered ring. Let's see here. You guys want to try a question of stereospecificity? Let's do that. Okay, question number 32 says, what is the major product of this reaction shown? So remember, the bromine and the hydrogen, the leaving groups, they have to be anti-periplanar to each other, and they are not anti-periplanar the way that it's drawn. You could either rearrange the sawhorse so that the hydrogen goes over here. So if you did that, and it will work in this case, you could just say CH3. Then you have your phenyl. Remember, C6H5 is the same thing as a phenyl group. So then we could put our bromine here, and then we could have our our hydrogen over here, which would mean the methyl group is down here, and then the phenyl is up here like this. So now you can see that the two groups, the bromine and the hydrogen, are in fact anti-periplanar to each other. So you can see that when the base, which is your hydroxide ion. So let me just pencil in a hydroxide here. Okay, so when the base comes along and you pull off this proton, you form the double bond and you lose the leaving group. You can see that the phenols are going to be on opposite sides. Okay, so one phenyl is going to be here, one phenyl is going to be here, and then the two methyls are on opposite sides. And so the answer is going to be C in that case. If you have to draw the Newman projection the way I taught you, so if you imagine your eyeball is looking at it this way, that totally works as well. You could say, okay, I've got the methyl group up here, I've got the phenyl over here, I've got the bromine down here, and in the back I have the proton over here, I have the methyl group over here, and then I have the phenyl down here like this. So if you rotate it, excuse me, so that the hydrogen is over here, so then we end up with something that looks like this. Not a very good circle. But anyhow, where you have the methyl group, where you have the bromine is going to be over here. My phenyl is over here. My methyl is up here. Now you've got the proton in the right place. And you've got the methyl group down here. And you've got the phenyl group here. So you can see that the phenyl groups are opposite to each other and the two methyl groups are opposite to each other. So once you do the elimination reaction, you end up with, the same compound that I just drew, which was this compound here. You end up with the trans compound like that. So remember, this reaction is stereospecific, okay? And the two, the proton and the hydrogen have to be what? They have to be anti-periplanar. All right, let's backtrack. Let's try number 31, okay? Let's try number 31. It just says which one of these represents the proper flow of electrons or the proper mechanism for the E2 elimination. So I'm taking this tosylate here and I'm treating it with, so if you have C2H5O, that's the same thing as ethoxide. Okay, so this is just NaOET. This is sodium ethoxide here. So if I'm doing my elimination, could anybody tell me which one of these looks like the correct mechanism? A, B, C, or D? Which one of these looks the most reasonable for an E2 reaction? This is an E2. Yeah, it's A, isn't it, Jenny, right? A is by far the best answer. I mean, it's the only right one. I mean, if you look at B, I would just put like, what is this? I'm not really sure what kind of arrow that is. You know, maybe the person had too much wine or something when they were doing organic chemistry. I don't know, but this curved arrow was way off in left field, right? A tail of an arrow should start on a pair of electrons. Same thing here. I can't tell what's going on here. This one has just got way too, I mean, this is not an electrophilic carbon, so I don't know why a nucleophile would attack that. And this one here, no idea as well, right? This is an E2, right? This would be step by step. This is an E1, and this is not the mechanism, okay? This is the mechanism here, right? You extract the proton, form the double bond, lose the leaving group. There we go. Looks good to me. So this is the proper mechanism of an E2 reaction.